Okay, I'm going to get to approximate solutions to differential equations, but I want to start with the relationship between a differential equation and its solution. Okay, so here's a differential equation, and I'm going to graph one particular solution, so that's going to be x as a function of time, since the variables in this equation are t as the independent variable and x as the dependent variable. Okay, and so let's say a solution to this differential equation looks like this. What does it mean for this curve to be a solution of this differential equation? It means that if we go to any particular value of x, here or here or here or here or here, it doesn't matter what value we choose, and if we compute f of x at that value of x, and then we head over to the solution curve, and we check what the slope is at that point, well, dx dt, the slope of the solution curve, is supposed to be given by f of x. So this slope and f of x at this point need to be identical for this to be an exact solution of the differential equation. And they need to be identical at every single value of x, where x is a continuous real, x is continuous, it's drawn from the reals, it can be any number here. It's not that they match at this point and this point, it's this point. They match at literally every single point along this curve for this to be an exact solution of the differential equation. Now consider some particular method of approximating a differential equation. This method of approximating is called Euler's method. And with Euler's method, we say, imagine we know the value of x at some point, and we want to estimate the value of x at some other point. So we know the value of x at this point, t, and we want to estimate the value of x at this next point, t. We're going to take our current value, and we're going to measure the slope at that point, and we're just going to move forward by that slope for this amount of time t, and this will be our estimate of what happens to the solution. So f of x sub n delta t. This is, where this little distance is delta t. This is a method of attempting to draw an approximate solution to the differential equation. Does this approximate solution make sense? We looked at this the other day, and we had this really nice argument that the change in x is equal to f of x sub n delta t, and that we can think of this as delta x. So this implies delta x divided by delta t equals f of x sub n. And if we were to take the limit as delta t goes to 0, then this would become dx dt, and this would become f of x. And so in the limit where these time increments become very small, this discrete approximation, this discrete map, converges to this differential equation. So this discretization is pretty similar to the original differential equation. So imagine we have an exact solution that looks like this, and we're using this algorithm to create an approximate solution. So we start at this point, and we compute the slope at this point, and we multiply times the delta t that we want to use. So let's say we're taking time increments about this big. So that gives us, we have a slope here, and we step forward at this slope times this amount of time, and add it on, and we land at a new point. And then we do it again. We use this function to compute the slope at this value of x, and we step forward in time, and then we do it again. And as delta t gets small, the error in this also gets small. But what are the sources of error? On an individual step, this point that we land at is not exactly on the solution curve, and so there's some error associated with the fact that delta t is finite instead of infinitesimal, and we have an error on an individual step. In addition, when we take a second step, we're starting from a point that's not actually on this solution curve. And so the slope that we get at this point is different than the slope that we would get if we had found the right point on the solution curve. So there's two sources of error here. One is sort of a type of cumulative error, where over time we're more and more off from where we belong, and the actual slope that we compute is thus more and more off from the slope of the exact solution at that same point in time. And in addition, so that's one error, this kind of type of cumulative error. The other type of error is like this local error. On every single step, we're not getting to exactly where we would want to be if we were mirroring the exact solution. How could we reduce this error? The way to reduce this error is get this estimate of the slope to be quite a bit better. And so the standard first method for doing that is to use something called a predictor-corrector. Let's say I take this first point and find the slope and land at the second point. Okay, well, I could just go forward and find a new point from this. Or I could say, wait a sec, now I have an estimate of xn, and I have an estimate of xn plus 1. Instead of just using the slope at xn, why don't I use the average of the slopes that we get at these 2 points? So at this other point, we got a slope that looked like this. Why don't I take the average of this slope and that slope and use it to project forward? And that would give me something like this. So that's the predictor-corrector. We're predicting a value for xn, and then we're using that value to help us correct our prediction. In an algorithm, it looks like this. X temporary n plus 1 is equal to x sub n plus f of x sub n delta t. And then x actual n sub 1, the point we'll actually use, is equal to x sub n plus 1/2 f of x sub n plus 1/2 f of x prediction sub n plus 1, all times delta t. So instead of using f at the initial point as our slope, we're using the mixture of these two slopes as the slope that we actually use to find our new point. The initial method up here is called Euler's method. And this method down here is called improved Euler's. We can take these methods even further. Like, okay, here's an example. Time x. We start at a point, and let's say we want to traverse this distance as delta t. Well, let's use our initial slope to go halfway and learn the slope at this new point. Then let's use this new slope, and just this new slope, to re-estimate where that point should be. At this new spot, we can measure yet another slope, and we can use that yet another slope to go, these green lines are supposed to be at the same angle, to go all the way the span of delta t. And so that is, that's a bunch of steps where we start with an initial slope k1 equals f of xn, and we use it to go halfway. And then we create a new slope, x2 equals f of delta t over 2 times k1 plus xn. So we used k1 to bring us to this point, and we found a new slope there, and we're going to use that slope to come halfway yet again to produce, and then once we get there, we're going to produce k3, and then we can use k3 to step all this distance, and once we get there, of course, we might measure the slope again, and we're going to call that k4, and instead of using a weighted average of just 2 slope estimates, we could use a weighted average of all 4 of these slope estimates to estimate our new x sub n plus 1 An algorithm that does this is called the RK4 Runge Kutta algorithm. And we'll talk more about why this Runge Kutta algorithm or this improved Euler algorithm might have lower error than this simple Euler method when we're trying to approximate the exact solution of a differential equation. What's the upshot? We now have 3 ways to create a discrete approximation. To the exact solution. These ways are all maps instead of differential equations. Why do we want maps? It's very easy to program a map in a computer. This is a super old school notion of a computer because I just gave it a giant monitor. And once we program that map into a computer, it's straightforward for the computer to solve the map for many different initial conditions. And so the computer can, if this is time and this is x, give us this approximation and this approximation and this approximation and this one and this one. And by asking the computer to start at lots of different initial conditions, using a computer can help us get a sense of all the different behaviors that the solution of a differential equation has. So creating these discrete approximations opens up the possibility of computational or numerical techniques for getting an impression of how the behavior of solutions to a differential equation.